Hello and welcome to this new lecture on compressible flow. So in this lecture we'll talk about the geometry of a converging diverging duct, and we will start from the equation that we've developed in the previous lecture. We said that dA over A is equal to minus dV over V multiplied by 1 minus the Mach number squared. So in the previous lecture we've investigated the two cases. In one case where the Mach number is less than 1, and we saw the variation of the velocity with respect to the variation of the cross-sectional area. And also we took another case where the Mach number is greater than 1. However, we did not consider the case where the Mach number is actually equal to 1. So if we take Mach number equal to 1, obviously the right hand side of this equation will be equal to 0, and you will see that dA over A is equal to 0. So in fact now we can say that the sonic condition, Mach number equal to 1, will happen when the derivative of the area is equal to 0. And we know of course that when the derivative of a certain quantity is equal to 0, that means that this quantity is either a minimum or a maximum value. So here we can say that the sonic condition will happen either at the minimum area or at the maximum area. So let's write this down. The sonic condition will happen either at minimum area or the maximum area. So to see if it is possible for the sonic condition to happen at the minimum area or the maximum area, we will take in fact two geometries. So we will start with the converging diverging duct geometry, and also we will consider another one which is quite the opposite of this geometry. In fact, we will consider a diverging converging duct instead of a converging diverging duct. So let's start with the converging section followed by a diverging section. And you can see that for a converging diverging duct we have this location where the area is minimum. So this is the minimum area, and in fact we can call it also the throat of the converging diverging duct. And we will take two cases. So the first case, we will consider subsonic flow entering the converging diverging duct, and in another case we will consider supersonic flow entering the converging diverging duct. So let's start with subsonic flow at the inlet, and we will draw the Mach number distribution and the pressure distribution along this duct. So let's extend this line here to indicate the location of minimum area, and we will also draw a line to indicate the value of Mach number equal to 1. Now, starting from subsonic flow condition at the inlet, we know that the converging part here will act as a nozzle for subsonic flow. So the Mach number will increase until it reaches a maximum value at the minimum area location. So you can see here that the fluid is approaching the sonic condition at the minimum area location. However, let's say that the flow will stay subsonic at the minimum area location. So if we continue in the diverging section will act as a diffuser. So the Mach number will decrease again in the diverging section. So this is the Mach number will stay subsonic, and we can conclude here that the sonic condition is possible at the minimum area location. So the sonic condition is possible at minimum area or at the throat. Now, if you want to draw the pressure distribution, as we said that the pressure distribution will be the opposite of the velocity distribution. So we'll have a distribution like this. The pressure will decrease until it reaches a minimum value at the minimum area location, then it will increase back again in the diverging section. So this is the pressure distribution, which is opposite to the Mach number distribution. Now, if you consider a case, for example, we will take a subsonic flow at the inlet of this converging diverging duct. However, we will take a higher velocity here, and let's say that the flow will reach sonic condition at the minimum area. So there is a possibility to have this transition to the supersonic condition in the diverging section. And we said that the diverging section will act as a nozzle for supersonic flow. So here the Mach number at the exit will reach values greater than 1. And in fact, in this case, we call the converging diverging duct, we call it a converging diverging nozzle. A converging diverging nozzle. So a converging diverging nozzle will accelerate the flow from subsonic up to the supersonic speeds, and this is only possible because the flow has reached the sonic condition at the minimum area location. So to go from subsonic up all the way to the supersonic, at some point the flow needs to reach the sonic condition. So a converging diverging nozzle, we have acceleration from subsonic to supersonic speed. And if you want to draw the pressure distribution, so since the Mach number here is continuously increasing along the duct, the pressure will have an opposite variation trend. So the pressure will be continuously decreasing. So starting from here, the pressure will decrease till it reaches a critical value at the throat. So this will be P star. So remember, at the sonic condition, the fluid will have a critical properties. It will have P star, T star, rho star. Okay. Then it will continue to decrease until it reaches a minimum value at the exit of this converging diverging duct. So the pressure here we call it the back pressure PB, and the back pressure that corresponds to supersonic flow condition in the diverging section is called the design pressure. So this is the pressure that is suitable for this transition to supersonic speed. And in fact, you will see later on, and we will talk about this in more details, that if you change this back pressure, there could be some situation, for example, the flow will reach the sonic condition at the minimum area. However, it will go back to the subsonic condition in the diverging section. So all this depends on this back pressure at the exit of this duct. Now, we will take also a second case where the flow will be supersonic at the inlet of this converging diverging duct. And also we will draw the Mach number distribution and the pressure distribution. So this is the location where the area is minimum, and here we have the reference value for Mach number equal to 1. Now, starting from supersonic flow, the converging section will act as a diffuser, as we said, for supersonic flow. So the velocity will decrease and the Mach number will decrease. So the Mach number will decrease and it will reach a minimum value at the minimum area location. And if the flow stays supersonic at the minimum area and we continue, the diverging section will act as a nozzle for supersonic flow. So the Mach number will increase in the diverging section, and here the Mach number will be greater than 1. And also in this case, the flow is approaching the sonic condition at the minimum area location. So we can say also that the sonic condition is possible at the minimum area, or is possible at the throat. Okay, So for the pressure distribution, we'll have this opposite variation trend. So the pressure will increase until it reaches the maximum value at the minimum area location, then it will decrease in the diverging section. So this is the pressure distribution. Also, we will take the case, for example, starting at a lower velocity at the inlet, there will be possibility, let's say the velocity is decreasing or the Mach number is decreasing until it reaches the Mach 1 at the minimum area. So there is a possibility now to transition back to the subsonic regime, and the diffuser, the diverging section will act as a diffuser for subsonic flow. So the Mach number will continue to decrease and it will reach subsonic condition at the exit of this converging diverging section. And in this case, we call the converging diverging duct, we call it a converging diverging diffuser. So a converging diverging diffuser will decelerate a supersonic flow back to the subsonic flow regime. So we have deceleration from supersonic to subsonic speed. Now, if we want to plot the pressure distribution, so since this is a continuously decreasing trend for the pressure, we will have a continuously increasing pressure. So the pressure will continuously increase. It will reach the critical value. So since, as we said, for the sonic condition, the fluid will have a critical pressure here, and the pressure will continue to increase in the diverging section until it reaches some back pressure at the exit of this duct. So you can see here in both cases, the sonic condition is possible, in fact, at the minimum area location. Now, let's consider the opposite geometry. Let's consider a diverging converging duct. Diverging converging duct. And let's plot this diverging converging duct. So we have this diverging section followed by a converging section, and also from the opposite side we'll have this geometry. So in this geometry you can see here that we have this location where the area in fact is a maximum. So we have this maximum area here. And also we will take two cases. So in the first case, we'll consider subsonic flow entering this diverging converging duct, and in fact we also call it a bulge. So a bulge corresponds to a diverging converging duct. So for subsonic flow entering this bulge, we will draw the Mach number and the pressure distribution. So this is the location where the area is in fact maximum, and this is the reference value for the sonic condition, the Mach number equal to 1. So starting at subsonic condition at the inlet, so here we have this diverging part. So the diverging part will act as a diffuser for subsonic flow. So the Mach number will decrease until it reaches a minimum value at the maximum area location. And in fact here you can see that the flow is moving away from the sonic condition at the maximum area location. So the sonic condition in this case is impossible at the maximum area. So now the fluid will stay subsonic at the maximum area. So the converging part will act as a nozzle, so the Mach number will increase in the converging section. So the Mach number will stay subsonic along this diverging converging section. And if we want to draw the pressure distribution, we'll have this opposite variation trend. So the pressure will increase until it reaches this maximum value at the maximum area, then it will decrease in the converging section. So the most important conclusion here is that the sonic condition is in fact impossible at the maximum area. location. Okay, now let's take the case where the flow enters as supersonic flow entering this bulge. So let's draw the Mach number distribution and the pressure distribution. Also, this is the location where the area is maximum, and this is the reference value for Mach number equal to 1. So entering as supersonic flow, we have this diverging part. So for supersonic flow, the diverging part will act as a nozzle. So the Mach number will increase in this case, and it will reach a maximum value at this maximum area location. So also here, the flow is moving away from the sonic condition, and the sonic condition in this case is impossible at the maximum area location. Now, the flow will stay supersonic. So the converging part here will act as a diffuser for supersonic flow. So the Mach number will decrease in this converging section. Now for the pressure distribution, we will have a pressure that will decrease to reach a minimum value at the maximum area location, then it will increase again in the converging section. So this is the pressure distribution. And also here, the important conclusion is that the sonic condition is also impossible. Sonic condition is impossible at maximum area. So the most important conclusion is in this lecture is that only at the minimum area we can have the sonic condition, and the geometry of a converging diverging duct can act in fact as a nozzle. So it can accelerate a subsonic flow up all the way to the supersonic condition, passing by the sonic condition at the minimum area. And also the converging diverging duct can act as a diffuser by decelerating a supersonic flow all the way to the subsonic condition at the exit of this converging diverging duct. And this is only possible because we have this possibility of sonic condition at the minimum area.